All right, it is 12 o'clock on the dot, and I'd like to get started. Thank you all for continuing to be with us all day. This is going really well so far. Just a quick overview before we jump into the Student Lightning talks. During this block, we'll start with these talks. We'll do the ISRU Viper session, and then we'll jump back to missions. We have Masaki Fujimoto at the end. And then while the discussion is going on, we will also start the poster. So people who want to stay and follow up with questions, please do. And then people who want to move on to the poster session may do that as well. So with that, I will get started with the Student Lightning Round talk. Each student has 1.5 minutes to introduce themselves, their poster, their work, and to advertise for you to come visit them. Most of these presenters are in the session today, but maybe not all of them. So check the poster listing. I would also like to add, while I'm thinking of it, to please check the poster listing online at the Survey website, because we have been getting some changes today as to which posters. So both the sign-up sheet and the online system are being updated regularly. So you'll see if anybody had to withdraw. We've had a few people with illnesses. Okay, and with that, our lineup today is here, and I'm going to jump right in with Mason Bell. So Mason, go ahead and turn on your microphone.
Hi, everybody. Thanks, Kristina. Can you hear me?
Yep, we can.
All right, perfect. So hi, everybody. My name is Mason Bell, and I'm actually here with Arun Kumar and Phaedra Curlin from the University of Colorado Boulder. And we are presenting our lab's work on robotic assembly recovery using virtual reality training for low latency lunar applications. So with coming goals to create a sustainable human presence on the moon, the call for real-time telerobotic operations has never been greater. Current high latency applications on foreign bodies leverage command sequencing to communicate with the rover from Earth. On top of this, hardware duplicates are utilized on the Earth's surface to recreate problems that the rover runs into. These are then used to develop solutions in a risk-free environment. As we move forward into the real-time operation realm, and with current stereo imaging technologies being able to provide real-time physical to virtual environment modeling, we intend to present new methods of failure recovery leveraging VR and AR. By developing our virtual recovery sandbox, we intend to create a virtual space representative of the rover's current state and environment, with the ability to troubleshoot problems as the operator standing next to the robot. By comparing our model to current failure recovery methods, we intend to assess how virtual recovery may supplement the operator's solution development for assembly failure whilst leveraging technologies already accessible to us. And our poster is actually being presented today, so come join us later. Thank you.
Thank you. Okay, now we will move on. If my slides will cooperate. They're just not cooperating. Okay, Anthony, take it away.
All right. Hi, can everyone hear me?
Yes, a little bit faint, but so maybe speak up just a little bit.
I can get a little closer to my mic. All right, so hi everyone. My name is Anthony Carroll. I work at the Institute for Modeling Plasma, Atmospheres, and Cosmic Dust at CU Boulder. And part of what I do at Impact is I study electrostatic dust lofting, which is basically dust regolith on airless bodies can be exposed to UV radiation or solar winds, and they eventually gain a charge, and the dust particles will eventually repel each other, overcoming cohesion and gravity, and loft and may become mobilized and maybe loft away. So this is really cool because it has a lot of natural phenomena that we think can be explained by electrostatic dust lofting, like the lunar horizon glow, dust ponding on comets and asteroids, and even the lack of fine-grained regolith on some asteroids. And so my poster is about measurements of initial launch velocities of a laboratory simulation for this process. So if that sounds interesting, please come check me out. Thanks.
All right, thank you very much. And let's see if we can move to the next slide. Okay, Rushik, are you there?
Hello, can you hear me?
Yes, we can. Thank you.
Hello, Namaste. I am Rushik Chandrachud from India. I am pursuing BSc from BK Birla College, Kalyan, which is affiliated to Mumbai University. Instead of talking in conventional manner, I would like to draw your attention to something different, yet important, and something crucial. When I was listening to some of the presentations earlier, I found that some of the presenters there was a particular slide for sustainable development. I was glad that this aspect was emphasized and considered carefully by the space explorers. Even I have considered this aspect for the reusability and sustainable development while developing my Lunar filter, which can provide mechanism for the filtration of lunar dust over lunar surface. So I would like to mention that seriousness of this statement that even if we manage to extract helium-3 from the lunar surface, our coming generations would have equal access to the resources which are being used currently. Also, they shouldn't run out of resources and they should not face necessity of finding the alternatives. Sir, I thank Survey organization for giving me chance to represent myself on this forum. And also, I wish everyone all the best at the end. And you can come and shake my poster at poster number 31. Thank you, everyone.
Thank you very much. Appreciate that. Okay, and now Ashley.
Can you hear me?
Yes.
Okay. Hello, everyone. My name is Ashley Clendenin. I'm a second-year grad student at Georgia Tech working towards my master's in mechanical engineering and my PhD in physics. I work on the Reveals project, co-advised by Dr. Tom Orlando and Dr. Peter Letzenheiser. My research focuses on using solar irradiation to drive in situ resource utilization, or ISRU processes, primarily the thermal extraction of water and the thermochemical extraction of oxygen or other raw materials from the lunar regolith. The lunar environment is ideal for utilizing solar to drive ISRU because it has none of the problems that complicate the use of solar on the Earth, like attenuation due to the atmosphere or solar blocking due to clouds. This solar irradiation is even more efficient if we concentrate it using one of the three main concentrating technologies: trough systems, tower systems, or dish systems. To study the thermal or thermochemical extraction of materials from the lunar regolith, modeling and some preliminary experiments have been performed. One particularly interesting thing discovered in this research is that the thermal extraction of water, if not done carefully, could have harmful or even potentially fatal side effects for astronauts involved in the process. If this is something that you want to learn more about, you can come talk to me at my poster, which is Concentrated Solar-Driven In Situ Resource Utilization on the Moon, poster 19 in poster session 1, which is later this afternoon. Thank you for your time, and I hope to answer any questions you have at my poster.
Thank you, Ashley. Okay, and now Ryan. Are you there?
Hi, everyone.
Great.
Hi, so my name is Ryan Galinkin. I'm going into my second year of graduate school over at the University of Central Florida. I'm currently working with Dr. Carrie, Donaldson, Hanna, and we're mostly working on thermal infrared spectroscopy on the mostly the lunar regolith. So it's quite interesting how the upper hundreds of microns is so important to these kinds of structures. A high porosity actually will affect how we view these incoming spectra. A lot of these things get changed, such as, gosh, I'm sorry, getting put on the spot here is hard. But basically, you get a lot of different effects, such as the small particle size and the low gravity and surface charges, and you get a stacked up structure. And because of this, you get very different effects on the moon than you would on Earth. So when we look at the spectra of things in our lab on Earth, they don't look exactly as they would on the lunar surface or on asteroids in general. And because of this, it's very important to understand how this upper surface layer works. So currently in my research, we're trying to see if we can actually determine how the absolute porosity has effects on this on these measurements. So because of that, a lot of people have had trouble doing this, and they've mostly dealt with relative porosities. But I'm trying to come up with a relatively trivial way to determine the absolute porosity. My poster number is 37, and find that interesting and want to figure out how I'm doing that with a compound light microscope, please tune in.
All right, thank you, Ryan. All right, now we will move on to Marina. Are you there?
I am, and if you can hear me,
Yep,
awesome.
go ahead.
Okay, so my name is Marina Gemma. I'm a PhD candidate at Columbia University, but I do my research at the American Museum of Natural History in New York City. My dissertation work broadly focuses on the spectral and geochemical properties of meteorites, but today I'll be telling you a little bit about my project, which is poster number 30, titled Multidimensional Characterization of Mineral Abundance in Ordinary Chondrite Meteorites. So quantifying representative mineralogy in meteorites often involves destructive techniques which sacrifice petrographic context in your sample. And traditional methods such as point counting aren't ideal to use because of the fine-grained nature of meteoritic samples. So to determine characteristic mineralogy for the meteorites that I work with, I've combined the non-destructive methods of three-dimensional computed tomography with two-dimensional X-ray element mapping of sample surfaces to ensure that the higher resolution two-dimensional maps and the mineral abundances that I calculated from those are actually representative of the bulk sample. So I've analyzed 20 meteorites spanning all petrologic types across the 3 ordinary chondrite groups, and the detailed petrologic analysis of these meteorites can be combined with their laboratory spectra, which is work I've previously presented at the Exploration Science Forum, to better characterize asteroids remotely. So if you'd like to learn more about this work, you can visit me later today at poster number 30. Thank you.
Wonderful. Thank you very much, Marina. And Kristen.
Hi, my name is Kristen Lusinger. I'm a 4th-year grad student at New Mexico State University, and I'm working with Dr. Nancy Chanover. I will be presenting a poster today introducing my project, which is modeling the vertical migration of water ice in seasonally shadowed regions. I actually grew up in a seasonally shadowed region up in Alaska, and so I was inspired to look at seasonally shadowed regions as a really great resource to understand vertical migration of water ice on the moon. We can use the regular disruptions to the sequestration process caused by the sunrises in the lunar summer in order to constrain the mixing rate during the time when the sequestration process was active. So if you want to learn more about my project, I would love for you to stop by. I'm at poster number 42, and I really look forward to hearing from you.
Okay, thank you. Pedro.
I'm here. Can you see me?
Yes, we can. Go ahead.
Okay,
Thank you.
perfect. Hey, everybody. My name is Pedro Montalvo, and I'm just going to briefly talk to you about the current research that I'm working on. I'm a PhD student from Auburn University, and I am co-advised by Dr. Toshi Hirabayashi and Dr. David King. Basically, our research explores regolith mixing depths by applying a numerical model that uses crater populations. And we can use that to map their distribution spatially in craters that host water ice, specifically in the lunar South Pole. So this becomes important because understanding such distribution and such distributions can let us know more about the thicknesses of how these deposits work, essentially, and could aid us potentially on future sampling techniques for future lunar missions. So my poster is number 31 in today's session. So if you got more questions, please stop by. I'll be happy to answer everything out. Thank you.
Okay, thank you, Pedro. All right, Gavin.
Oh, can you hear me?
I can hear you. I can't see you.
Okay, my camera seems to be acting weird, so I'm just gonna go ahead and talk and hope it fixes itself.
Okay.
Hi, my name's Gavin. I'm a PhD candidate with the Institute for Earth and Space Exploration at Western University in Canada. And I'm working with Dr. Catherine Nish and Dr. Gordon Zinsky, trying to understand more about lava flow, emplacement, and surface roughness on planetary bodies, particularly in the Moon and Mars. So on the Moon, lava flows is one of the best ways for us to try and understand past volcanic processes and interior magmatic processes. But unlike Earth, we still don't have a very large suite of data sets that allow us to look at the surface roughness of lava flows at different scales. So part of my research is to use terrestrial examples, which do have similar morphological properties to some lunar lava flows, in particular when you look at them through radar. So my poster, which is studying the lunar lava flow emplacement by quantifying the surface roughness of the Holuhraun lava flow field using synthetic aperture radar and LiDAR will be able to help us understand flow emplacement mechanics on the moon. So if you'd like to learn more about my work, my post is number 81, and I'll be presenting it today. Thank you.
Okay, thank you. And Michael, I think, is our last one.
Okay. Let's see, are you able to hear me okay?
Yes, we can.
Okay, awesome. All right, so hello everyone. My name is Michael Walker, and I'm a PhD student working with Jack Burns in the CU Boulder NEST team. And my research looks at the use of mixed and virtual reality technology for mediating and enhancing human-robot interactions. In terms of space exploration, this really means how can we leverage this technology to create new and improved interfaces for better facilitating surface telerobotic missions. These new technologies allow for enhancing and viewing collected data from these remote space robots in the full dimensionality of our world. Additionally, this technology presents a means of astronauts of the future to immersively teleoperate these robots, either from orbit or the safety of a space habitat or a surface habitat, and provide enhanced methods of robot control for manual teleoperation missions or manual error recovery for missions featuring robot autonomy. Currently, the disadvantages, such as operator fatigue or the required infrastructure, seen with these new interface technologies featuring head-mounted displays have not made a strong enough case yet for use in current space missions. However, it is my hope that with my work and work like it, will provide designs and justification of adoption of these new interface technologies for future space missions. And today I'll be presenting a poster during the first poster session. It'll be poster 21. And if you'd like to hear more or talk more about this topic, I'd love to see you there. And thank you for having me.
Thank you. Let's just make sure I was right. Okay, so I thank all of you. You did a great job. And I encourage all of the attendees to join them at the poster session today.